Yeah, hello, my name is Andreas Krebbel. I work on AI and compilers for Linux on zSystems. And I have the pleasure to talk about a super interesting new feature of IBM Linux 1 and IBM z16, of course, the integrated AI accelerator. So a brief introduction on the accelerator. Nowadays, most of the AI workloads are either executed on CPU or on GPU. And the integrated accelerator is somewhat in between these two approaches. It is a centralized accelerator which sits on the chip alongside all the cores, but it's not really part of the core. So it is shared among 8 of the cores. It is as close as you can get to the cores, so it really participates in the cache hierarchy. So in the ideal case, if you have a business application producing data, which then should be consumed by an AI workload, ideally that data does not even need to go out to memory. The AI accelerator can directly fetch it via cache hierarchy from the other core. And an alternate approach would have been to really add more instructions into each and every core, but we decided to make it a centralized accelerator because we think that not every core will run an AI workload. And these instructions you would have to add are very specific. And because of the very small and specific data types they are using, they are usually not useful for general purpose applications. So it would be a waste of chip space in each core because most of these cores would not actually run AI applications. But instead, if you have an application where most of the threads do the business logic and all that, and you have just a couple of threads doing actual AI, these AI threads can utilize the full power of the AI accelerator then. And that's a huge advantage of that approach, I think. But how do you talk to the accelerator? There is a new instruction implemented on the core, the NNPA instruction, Neural Network Processing Assist instruction. And this is an instruction which is issued on the core and is backed by millicode, and that millicode drives all the operations on the accelerator. So the millicode fetches the memory needed for the operation on the accelerator and then triggers all the operations on the accelerator. So the NNPA instruction is basically a memory-to-memory instruction. So you give it a bunch of pointers for input tensors and output tensors and a PARM block which describes the actual functionality. And then you start the execution. The millicode in the NNPA instruction also makes sure that no other core can use the accelerator at the same time. So there's some kind of blocking implemented in there. And by the way, because the work on the accelerator is actually driven by millicode which runs on the core, by that we inherit all the nice properties of the IBM Z processor like virtualization and address space protection and all that. Okay, let's have a look at the details and why that accelerator is so powerful. The accelerator consists of mainly 2 parts. The first part is a 2-dimensional array of compute engines, so-called processor tiles. And this compute array is used for matrix multiplication and convolution operations. And then there's another part that's a 1-dimensional array of compute engines for complex CF, complex facility, or complex functions. And this array is used for things like activation functions and so on. And because you have these 2 parts separately on the core, that means that you can execute matrix block operations and activation functions in combination. So we have complex operations on the accelerator like convolution, which is combined with an activation function like ReLU. So you can issue that as a single operation on the accelerator. The accelerator has a raw performance of about 6 teraflops. So we have 32 of these accelerators in the whole system. That adds up to about 200 teraflops in the system. Since the accelerator sits alongside all the cores, it also accesses memory by the same means a core would do. So it is able to fetch memory from the cache hierarchy with about 200 gigabytes per second. The internal routing and formatting network of the accelerators has a bandwidth of about 600 gigabytes per second. An interesting feature and an interesting property of the accelerator is that it's not just something which helps you a bit with matrix multiplication. It is actually capable of executing complex operations, like, for example, the bigger part of an LSTM cell. If you look at an LSTM cell, long short-term memory, so it's super popular right now for when it comes to natural language processing and all that. And such a cell consists of several matrix multiplications and activation functions and element-wise operations. And the bigger part of that operation is a single operation on the accelerator. And this is really what makes the accelerator so powerful. This table shows a list of operations as they are available on our accelerator. And as I mentioned, LSTM, GRU, there's support, of course, also for matrix multiplication, several activation functions, and so on. The nice thing is these operations are driven by a Pico code. That's code which is shipped as part of the machine, as part of the MLIR code. And that also means that you can update that MLIR code and that Pico code as part of a MLIR code update. So there could even be updates in between GAs to just add more functionality to that, as long as the hardware is capable of doing that. This is one of the benchmarks we have published at Hot Chips, for example. And that shows the performance of a credit card fraud model. We have developed, IBM Research has developed that model together with a global bank. And what that chart shows is on the x-axis, the inference executed per second, so that's basically the throughput on a log scale. On the y-axis, you have the worst case latency of one of the inference jobs. And as you can see, with the blue line, once you increase the number of inferences per second, so you need more bandwidth in the system, of course, the worst case latency at a certain point goes up. And the nice property of our system is that it's so much balanced that you can always push it down to that 1 millisecond worst case threshold by just adding more AIUs. And this goes up until you have basically the entire system doing AI or executing that AI job. So if you have the workload running on actually 32 chips, so that's really leveraging all the accelerators in the system, you can still do 3.5 million inference jobs and have a worst case inference time of about 1 millisecond. And that's really what resonates well with many customers, because that's really a property you cannot get with other systems right now. That's illustrated here a bit more. So for example, if you run an AI model on CPU, and for example, you want to increase accuracy, the execution time goes up exponentially. And once you have outgrown the bandwidth of your system, the latency will go up, and you will not be able to meet your SLAs anymore, and you exceed a certain threshold you might need for your transaction, for example. One solution to that might be, okay, then I try to offload that to a remote system with GPUs or something like that, a PCI Express attached accelerator. But thanks to all the network traffic, the additional network traffic, and the additional overhead to device drivers and memory pinning and all that, what is needed there, again, you're not able to meet your SLAs or fit it into the transaction time limit. And the AI accelerator really is a solution here. And we have seen that with several customer scenarios already. It is powerful enough to execute medium-sized models very fast and with low latency, because it sits so close to the cores. Another use case is if you have to deal with sensitive data. Of course, sensitive data reside on IBM Z for a very good reason. And if you want to do AI with these data, there is no point in sending these data around to the net and having to encrypt everything, have to make sure that everything is compliant and all that. That adds a lot of complexity, and in the end, most likely, latency goes up by so much that you do not really want that solution. Instead, with the AI accelerator, try to bring your AI application onto the Z platform leverage the accelerator, and work with the sensitive data directly where they reside. That's what IBM subsums under the data gravity term. Okay, when we talk about exploiting the AI hardware in Linux on these systems, of course, I already talked about the integrated accelerator a bit, but since IBM Z13, we also have SIMD instructions. SIMD stands for single instruction, multiple data, and the idea is basically to exploit data flow parallelism in code. So that's nothing completely new. All the other general purpose processors have that as well. So Power, x86, you have AVX, you have a Neon instruction set with ARM, and on Power you have VSX, and so on. And since IBM Z13, we have 32 128-bit wide vector registers, and we have a rich instruction set of operations which deal with these data. And since IBM Z14, we have also support for single precision floating point numbers. So with a 128-bit vector, that makes 4 elements per vector. And with such an instruction, you can do an operation on all these 4 elements in a single operation, a single instruction. And of course, we also have to keep that in mind when it comes to exploiting hardware in AI frameworks on Linux on these systems. Okay, what is our strategy here? In order to make an AI framework available on Linux on this system and optimize it well, we have basically 3 stages. Of course, the first stage is to bring it onto Z and make it working there. And for most of the open source packages, it works out of the box. But then there are, of course, a few cases, and the biggest issue here still is endianness, of course. So it's enabling these frameworks often means fix endianness bugs or enable protocols to be endianness aware. The second stage is make use of the SIMD instructions. This usually comes with a moderate effort because most of these frameworks are prepared to support SIMD instructions, simply because all the other architectures have it as well. So there are interfaces available, and there are means to make that, to help implementing this. And the ultimate goal for all the frameworks, of course, is making use of the integrated AI accelerator, but this comes with a bit bigger effort. And the idea here is that we try to bring as many frameworks as possible onto our platform. For a certain amount of frameworks, we do SIMD optimizations, and for the critical frameworks, we focus on making it available with the AI accelerator. That chart shows just a selection of AI frameworks and tries to demonstrate the progress we are doing here. And as you can see, there are very famous frameworks which all work very well already on Linux on this system, and many of them are also enabled with SIMD instructions. And on the lowest layer, we have things like the deep learning compiler, Snapml, and Tensorflow enabled already for the integrated accelerator. The rest of the presentation basically will be about explaining these 3 things and how we optimize that for the integrated accelerator. With regard to SIMD optimization, for example, OpenBLAS and Eigen and NumPy, these are really central pieces of an AI stack. And making use of SIMD instructions made a huge difference here. And it's not only about that particular library, but also about many different AI frameworks which actually depend on that. So if you optimize OpenBLAS, you also accelerate scikit-learn, for example. You accelerate NumPy and OpenCV. These frameworks still are only on the first layer because there is optimization opportunities beyond that. So they also have other arithmetic implemented which could make use of SIMD instructions. Before talking about exploiting the AI accelerator, I think I have to explain what Onyx is. Onyx stands for Open Neural Network Exchange. It's an AI model interchange format. It is an open standard. It is backed by the Linux Foundation, and really is a game changer in the AI frameworks and in the AI stack. Because in particular for us, it enables us to bring in new frameworks and new things into that stack without forcing everyone to re-implement their AI solutions with a new API, for example. Onyx allows importing and exporting machine learning and neural networks between different frameworks. So it's not only about deep learning, so there are importers and exporters for TensorFlow, PyTorch, and so on, but it's also useful for machine learning, and we use that to implement things like Snapml and the DLC deep learning compiler. Okay, let's talk about Snapml. Snapml is a library developed by IBM Research, and it is used for machine learning workloads. In particular, it is used for, it is very strong with decision tree-based models. And what Snapml is doing is it maps decision tree computations onto matrix operations. And that makes it particularly useful in combination with things like AI accelerators, because they are really good in doing matrix multiplication. And in particular, with our AI accelerator, we have a very specific matrix multiplication tailored for that particular use case. So you do a matrix multiplication and a comparison against another matrix in one go. And that maps perfectly to what Snapml is doing. Snapml is not open source, but can be used free of charge. You can just do in your Z environment pip install Snapml, and it will be there. It has an API very similar to scikit-learn. And basically add model load time. You say, okay, I want to execute that or run that model then on a GPU or on an AI accelerator or on a CPU. But instead of using the API of Snapml, you could also, as I said, convert your machine learning model to Onyx, load it into Snapml, and execute it there without changing the application. Next is the deep learning compiler, or Onyx MLIR. These are, I use these terms as synonyms here. Deep learning, DLC, deep learning compiler, that's the term IBM is using for that. But it's also developed by IBM Research, but it's fully open sourced. And the open source project is called Onyx MLIR. And the interesting thing here is, the idea is to feed an AI model into a static compiler framework and turn it into an executable you can run on the hardware directly. So you take an AI model, convert it to Onyx, feed it into that compiler, and the result will be a shared library you can directly use on Linux on these systems. You can use it from Python workloads, from Java workloads, and of course C and C++. It has a well-defined entry point, and so you can link it to your application, call that entry point to do the AI computation. And even beyond just trying to exploit the AI accelerator, I think that's also a value on its own. It allows a very tight integration of the AI model with your application, no dependency on AI frameworks anymore or anything. You can really bake the AI model into your application. The deep learning compiler is implemented on top of LVM. LVM is, besides GCC, the other open source compiler available on Linux on these systems. We have both compilers support GCC. We have support for GCC since the very beginning, of course, but also LVM is supported for many years already on Linux on these systems, for graphics rendering, for example, on IBM C systems. And the DLC compiler is implemented on top of that. And it uses a new mechanism to implement language front ends for LVM, which is called MLIR. In that particular case, ML does not stand for machine learning. It's multi-level intermediate representation. And the idea is that during the front end stack, or as part of the front end stack, different abstraction levels of the language can coexist. That's in MLIR terms, it's called dialects. And so there are different dialects which represent different abstraction levels, which are useful for different kind of optimizations. So for example, on one abstraction level, you would rather like to have a matrix multiplication as a single operation, because then you can easily fold that together with other matrix operations. But on later optimization levels, you would rather like to see a matrix multiplication as a loop nest actually doing the computations, because you would like to reorder the loops to improve cache locality and things like that. And an interesting property of MLIR is that you can have in the same intermediate representation statements of different abstraction levels. And that way you can really reuse dialects from different languages and different optimizers. as long as at the very end you lower everything to LLVM-IR, and then it is fed into the static compiler framework and is compiled into a binary. As I said, it's fully open source. Just check it out, compile it. Compiling it is actually not that easy, but can be done, and it's described in the README. It's an interesting project. And of course, that compiler is also able to build code which runs just on CPUs. So it uses the standard language compiler backend for Linux on these systems, so it can build a shared library which runs just without the AIU. It has two flavors. It can build shared libraries for which need the AI accelerator, but it can also build libraries which run just with the CPU. Okay, TensorFlow. Of course, we have to talk about TensorFlow when we talk about AI. There are many more frameworks coming up, like PyTorch and JAX and so on, but when it comes to production workloads, so far TensorFlow is still number one. We have TensorFlow optimized for both things, both hardware capabilities we provide on IBM zSystems. So for quite some time, we have SIMD optimizations for TensorFlow. When you compute an AI model with TensorFlow and run it on the CPU, it is using the Eigen library as a backend. Eigen is not really a library, it's rather a bunch of C++ header files. And all the computation and all the optimizations and all that happens during compile time. For the AI accelerator, we have a chain of layers which map these operations of the generic compute graph to operations on the AI accelerator. And in order to do that, they cache operations when they are sent to the device, and then try to do fusion of operations or insert optimizations there. In the end, the interface to talk to the accelerator all goes through the zdnn library. The zdnn library is a low-level driver library for the AI accelerator, and the idea is that it encapsulates all the operations of the accelerator. So the idea is that every application making use of the AI accelerator is linked against that library and is using the accelerator through that library. It's fully open source, it's available in many distros, and it also provides utility functions in order to convert tensors into the specific format of the accelerator and convert tensors provided by the accelerator back to the standard format used by the frameworks. Okay, I will skip the SIMD optimizations we did for OpenClass. So this example just shows how typical AI use cases map to what we have on Linux on these systems. So all the brown cases are standard machine learning use cases. You can execute or run these models with standard frameworks, with scikit-learn and so on our platform, but also with Snapml. And they will benefit from the CPU SIMD optimizations we have. For decision tree-based models, Snapml is definitely the right tool. You get a huge performance benefit by using Snapml in combination with the AI accelerator. And for deep learning models, you can choose between running them directly in TensorFlow. So the great thing about all these TensorFlow optimizations we did is they are all transparent to the application. So you have the same compute graph you're using on x86 or on other platforms and run it on Linux on these systems and all the optimizations will transparently be applied to that compute graph. So for deep learning models, you can decide to either run it directly with the TensorFlow optimized for AIU or for CPU if you want. But you can also decide to export that model to Onyx, feed it into DLC, compile it into a shared library which runs on IBM Z16 or on IBM Linux 1.4 and make use of the AI accelerator. One thing I would like to mention is Anaconda. IBM works together with the company behind Anaconda. Anaconda is kind of a distro within a distro framework with its own package manager and all that. It tries to be as self-contained as possible. It's you can imagine it is similar to what PyPy provides with pip install and all that, but it tries to be more independent from the operating system. So if you use pip install and all that, you usually still use the Python provided by the operating system, by the Linux distribution, and many of the standard libraries there. But for Anaconda, you have the Conda package manager, and when you install applications there or packages there, it usually comes all from Anaconda. And we work together with them to get in our latest optimizations and all that. So you would always get a consistent set of packages and versions across different Linux distributions on Linux on zSystems, but also across different platforms. So if you do the same on x86, you get the same NumPy version, the same OpenBLAS version, and all that. So Anaconda really helps to have a consistent layer for your AI application. I would also like to mention the IBM Systems Container Image Registry. That's a nice way to start with doing AI on Linux on these systems or on ZOS. This container registry provides images for deep learning compiler, for TensorFlow AIU, and for all these nice packages with all the optimizations provided by IBM, plus vulnerability checking and incident management and all that. So if you have questions with regard to IBM Container Registry, Joe Bostian would be the right guy. He's doing all that. Another way to work with AI on Linux on these systems is Cloudpack for Data, and that's really meant to be the premium product. It combines many, many open source frameworks with all the optimizations I just talked about. It is built on top of Anaconda, and it combines that with plenty of connectors to databases, for example. So you can, on the Cloudpack for Data page, you can find a list of connectors which help you to connect the data sources with your AI application. So we have connectors for Oracle, for DB2, for SAP, and all that. And it comes also with many interesting IBM products. So what's machine learning? And there's even DB2 in there. There's DB2 data stage, which allows you to sync a DB2 database from ZOS onto Cloudpack for Data to do AI with the data there. So that's really the premium solution. It requires Red Hat OpenShift right now. And yeah. So that's really the right product to bring data and AI stacks together on our platform. So on the last chart, just a summary of what I just described, the entry points for your AI journey on Linux on these systems. There's Cloudpack for Data as a premium product and the best combination of IBM products and open source components together with data providers. Then there's a deep learning compiler with its unique capability of turning an AI model into a binary you can directly run on Linux and IBM C systems. There's the Snapml library, which helps you accelerating decision tree-based models using the AI accelerator. And then we continue to work on many, many more open source components. And so, for example, if you found an AI framework which is super popular but doesn't run on Linux on these systems, right now, we are there to help. So we would like to set it onto our list and prioritize it to get it going. Here are just a few links if you're interested to read more about that. There's many more materials, so get engaged with us, and we are happy to learn about your potential AI use cases or what additional components you might need to make it happen with customers. Okay, sorry for rushing through that. It was a lot of material to squeeze into just half an hour. So, and I think we can start the Q&A session. Do you have any questions? Do we have time for questions? If you do not have a question right away, of course, I'm here at the conference, so approach me and I'm happy to discuss on these topics. Yeah. Yes, we are working with quite a bunch of customers, and it's still, the fraud detection is still a hot topic, not only for credit card, but many customers from the finance industry are interested in, also retailers, and detecting fraud is a hot topic. We are also working with some customers on image recognition. So there are companies from the health insurance area would like to detect anomalies in, for example, X-ray pictures. And all that fits super with IBM zSystems because all that is sensitive data, right? I mean, right from the start, we didn't really think about image recognition and all that as a proper use case for our platform because what we are not in the business of finding cat pictures or something like that, right? But thanks to these X-ray pictures and all that, and these sensitive data, completely new use cases are coming up. And actually, image recognition works really well with the Accelerator. We have that convolution operation there, and we have seen examples with 20 times faster execution of these models. That really works well. Yeah. Okay. Okay. So thank you very much.